Hi, it's Mr. Anderson, and this is Chemistry Essentials video 35. It's on the rate of reactions, or the speed of reactions. Now, some reactions we might think of as incredibly slow. In other words, the rusting of this train car is going to take years and years to occur, to fully complete that reaction, if it ever is completed. But if we wanted to speed that up, we could do it by increasing the surface area of that iron. And we do that in a hand warmer. A hand warmer is essentially a bunch of iron that has been shredded to increase surface area. And so when you pull it out of a bag, it's going to combine with the oxygen and it's going to create a certain amount of heat. And that happens really, really quickly. And so again, the rate of reaction is going to be different for the reactants and the products, but we also have a certain amount of control over that. And so in a chemical reaction, the rate is simply the number of reactants that are converted to products in a given time. And so let's say the red and the blue represent reactants, and we combine those together to make products. The more quickly that we can do that, the faster our reaction rate is going to be. And there are a number of things that are going to affect that. The concentration, in other words, the more reactants we have, the more quickly they're going to find each other and the faster that reaction is going to occur. And also the pressure, in other words, if we decrease the size of that vessel that they're in, then we're going to have more of those reactions going on. Also, it's going to be the phase that it's in. Clearly, if it's in a gas, in an enclosed container, we might have faster reactions than we would if it's a liquid. And then finally, environmental factors. Things such as temperature and surface area are going to affect the rate of the reaction as well. And so if we're looking at two reactions, the rusting of metal and the combustion of wood in this case, both of those are going to have reactants, and I've marked those as A, and products, and I've marked those in C. And so the rate of reaction is going to be represented in this formula right here. And it's really simple. It's not that complex. It's either going to be the negative change in the concentration of A. In other words, we're going to have a decrease in the amount of reactants over a given amount of time. Remember, delta is just going to be the change. Or we could measure it as the amount of products that are being created over time, because those are essentially going to be the same thing. The more reactants we have being consumed over a given period of time, the faster that reaction is going to be. And likewise with the products. And so how do we measure the reactants? Let's say I have a reaction that I want to measure the reaction rate. How do I actually know how many reactants are in there? Well, a great example of something you could do is to use Beer's law. And so in this reaction right here, what I'm doing is creating a copper sulfate solution. I'm shining light through it. And what I can do is I can vary the amount of concentration, and you can see that the amount of light that is being transmitted is going to decrease as we have more of the concentration. I could then start collecting some sample data. So let me change it from 50 to 75 to 100 millimoles. In other words, let me increase the amount of that copper sulfate solution. Generally, what you would do is start with a stock solution and then dilute it over time, and you can see that the amount of transmittance is changing over time. Now, if I wanted to graph that, let me graph the data that I've just collected. Now, right here, I've got the concentration on the x-axis, and then the transmittance. In other words, the amount of light that's allowed through that sample, and we'll generally use something like a calorimeter or a spectrophotometer to measure that. And now I've got my standard curve, and so you can see that as I increase the concentration, that transmittance is dropping off, and it's kind of approaching a limit. So what could I do is I could take a sample and I could measure the reactants. I could then stop it at different times, and I could figure out how much of it is actually being consumed. Once I know that, my millimoles, I could figure out the time it's taking, and I can figure out the rate of the reaction. Now, it's important that you understand what's going on at the molecular level. And so this nice little PHET simulation will help out. And so in this one, the yellow and the other two are going to represent the reactants, and there's products, and reactants and products. In other words, it's converting from reactants to products and back again. Now, this is working perfectly because they're lined up perfectly. In other words, every time they hit, there's a perfect reaction. But let me angle that initial shot. Now the reactant doesn't hit the other reactant perfectly, and so we can't convert it to those products. And so it's really important that we're lining them up. And so let me now get a number of those reactions. That was a little bit boring. So let me add a number of different reactants. We're going to call those reactants A. And now let me add a number of different reactants like this. And so you can see by increasing the concentration of those reactants, it's more likely for them to hit each other. But again, we're not getting that reaction occurring because we don't have a high enough energy. So now let me increase the temperature, and you can see that now we're starting to have reactions occur. And if I were to keep track of the amount of those reactants converting into products over time, then I have a pretty good idea of what's going on with the rate of reaction. So what things could affect this? Well, temperature. As we increase the temperature, the molecules are going faster, so they're more likely to run into each other, more likely to have that reaction. If there's more of them, a higher concentration, or if we squeeze them together, if we have a higher pressure, that's going to increase the rate of the reaction as well. And then finally, surface area is incredibly important. All of these are broken down to the level of the atom, but let's say we just had a big tablet filled with A, and it hadn't been broken down, just like that big train car at the beginning, it's going to take a long time for us to break down, and the reactions could only occur on the surface, and that would be a slow rate of reaction. And so did you learn to interpret the results of an experiment regarding temperature? Could you start by figuring out the amount of reactants and then measuring it over time? If you could, you know how to calculate the rate of reaction, and I hope that was helpful.